Hello and welcome everyone. I am Lorenzo Cardarelli, a quantum algorithm developer at Pasqal, and today I'm presenting one of the algorithms, a workhorse algorithm in the equality consortium, which is differentiable quantum circuits. It is an important algorithm because it aims at solving partial differential equations and stochastic differential equations, and therefore it applies to a large number of areas, from engineering to physics, research, natural sciences, chemistry. And together with partners at Equality, we have been developing the algorithm and applying it to use cases of industrial relevance. My presentation is divided in three parts. In the first part, I will present the algorithm, and then in the second part, I will give a sneak peek at applications of DQC to some use cases. This will be mainly touched upon in the second and third webinars, but it will be the ground for me to present some developments that we have been doing over the course of the during the course of this equality project on DQC. And to conclude, since Pasqal is a quantum company producing quantum hardware, I will give a compendium of the hardware architecture based on neutral atoms and how this allows to run digital quantum algorithms such as the DQC algorithm. All right, let's begin with the first part and talk about differential equations, which are central to many scientific fields, as I was hinting at, ranging from fluid dynamics to financial modeling and chemistry. Now, solving nonlinear, especially systems of differential equations, is often difficult, requests heavy computational resources. And the challenges lie usually in the nature of the equation, but can be enhanced by the dimensionality, the presence of nonlinearities, and the nature of this equation, whether or not it has rigidities or is numerically unstable. Now, classical methods do an excellent work at solving, let's say, all simple differential equations and also very complicated ones. Let's think about modeling air winds for airplanes. But the costs are at times prohibitive. If for solving the differential equation modeling at thermal fatigue in T-junction, it may take less than a minute, a few gigabytes of memory, so it's runnable on everyone's laptop. Studying the trajectory of a simple body is already more demanding, and we get to weeks of computations for studying, for instance, nuclear fuel assembly, or even to hit a wall and dealing with intractable problems when it comes to aerospace modeling. This difficulty has been the motivation for trying various approaches over the course of the years, and in recent times, of course, the community has given a go at machine learning, trying to see if there could be an edge over classical iterative methods. And perhaps obtain better simulations or reduce the costs. Now, the family of algorithms based on classical machine learning for solving partial differential equations take the name of PINs, physics-informed neural networks. These PINs are very much similar to the classical notion of neural networks and machine learning, meaning there is a neural network that models a function. Let's take a simple case of a function of time and one spatial variable, x, and a scalar codomain. So f of xt, and the output is a number, is a scalar. U of xt. Then what the neural network does is to take as an input via the two neurons in the first layer, the domain of the equation, and then output the value of the function at that point in the domain. Now, at the beginning, this network is, of course, initialized randomly, and therefore the output does not at all represent the solution of the partial or the differential equation. The training allows to optimize the parameters in the network in order for you to be a good approximation of the solution of the PDE. The key feature of pins is that the physics of the problem is embedded in the loss function, and that's the way by which the training is able to enforce this notion of the problem and train the network to model the solution. Calculating the loss requires the calculation of all the terms of the differential equation. In this case, we have a partial derivative with respect to time to x, and the second order derivative. Perhaps there is a term involving u, even in a non-linear fashion. And to calculate these terms, well, the u1 is given, simply a forward pass of the neural network, whereas for the other ones, one has to differentiate the neural network. Now, this can be done, the derivatives can be calculated in an approximate fashion, but this would introduce an error in the loss itself. Fortunately, with automatic differentiation, it's possible to calculate the derivative exactly. And therefore, the loss allows for a gradient-based search for optimal parameters, which introduces no elements of randomicity or error in the loss function. And yes, and the loss also is one possible and the most obvious criterion for convergence. So this left-hand side of the equation will be at the beginning modeled by the neural network, different from zero, larger than zero typically, and convergence is attained, perfect convergence is attained when this term is null, is zero, or when it's good enough, is below a certain error threshold. Now, since inception, pins have been developed a lot, now for nearly a decade. And these developments have definitely raised the bar of what pins can do. And recent reviews underscore the performance of pins and remark that they have been successfully applied to a number of problems of industrial relevance, and highlight how they are ready for tackling problems and that have indeed industrial relevance, and therefore appeal for economical appeal, appeal for business, and challenge classical methods, potentially reducing the costs and therefore, increasing gains for companies. Now, one has to say, however, that from a recent study from AWS, it emerges that despite the gain, this relative gain is consistent and remarkable, yet for solving very complicated problems such as aerodynamics and three-dimensional problems with perhaps supersonic shocks, still the costs are, well, not prohibitive, but quite high. So both with CPUs, so classical methods, and with GPUs, meaning with pins, we are in the range of millions of euros for the computations and hours for concluding an experiment, a simulation. So within the context of a search for alternative methods that might provide an edge or some form of advantage, quantum computing is definitely the latest kid in town, and of course it's worth giving it a try for the importance of the problems the relevance of the problems at stake. And Pasqal has developed and has designed and is developing a quantum algorithm to solve differential equations, which is called the differential quantum circuits, and it is, in a sense, a quantum counterpart of pins. In fact, we can see that it shares a number of features, structural with classical pins, though including also the power of quantum computing. Now, a brief recap: the structure of pins requires the embedding of a classical variable or the domain into a neural network, and then through automatic differentiation, it's possible to calculate exactly the derivative, and then optimization is steered by the loss function, which embeds the problem, the differential equation. The DQC algorithm follows this structure, and notably, it is able to guarantee the exact differentiation of the model function. So if in classical neural networks there is automatic differentiation, in the DQC algorithm, the derivatives are calculated exactly by means of exact differentiability of the model quantum neural network. And the classical neural network is replaced with a quantum counterpart. I'll get into the details of it in the next slide. But it follows the same behavior in the sense that it takes as an input the domain of the partial differential equation, points from the domain, and outputs both the function f of x, the model function, and the derivatives thereof. The parameters in the quantum neural network are trained similarly by defining the loss function and calculating with the updates by means of a gradient-based method. Okay, let's focus on the quantum circuit. The differentiable quantum circuit is, can take different shapes. This is a simplified version of it that presents the main blocks, the main elements of a DQC. The first element is the quantum feature map, which is it's a counterpart of what in classical neural network would be the first layer with two two neurons. If we have x and t, two variables, then there would be two neurons in the first layer. In the quantum neural network, there can be as many qubits. That's not the one-on-one correspondence, but multiple variables can be embedded. In this case, we have a simple one with only x, and the action of the quantum feature map is to apply typically single qubit gates to the register, to the initial input state, and the angle of these gates depend on the variable which is being encoded. So now, if the equation is the domain of the equation has more than one variables, one has to assign these variables in various forms, either on the same rotation with a combination of the of x and t, or by spreading the encoding over a different qubits of the register, meaning the first three can encode x, and then the rest can encode the variable t. Regardless of that, the second block is the block that takes care of modeling the approximator and make it as similar as possible, as close as possible to the sought-after solution. The gates in this case, just like in the feature map, are parameterized. So these operations here have a parameter theta, which can be the same for all, but that would not be too expressive, or can be different for each of the gates. And these parameters are trained and optimized by means of parameter shift rule, which is an equivalent form in the quantum realm of automatic differentiation. And then there is typically a stack of entangling gates in order to make things quantum, essentially. Otherwise, it's a classically simulable circuit. Now, the last part of it, what in classical neural networks is a output layer. Let's assume in this case that we have a simple function with a scalar function. Then in classical neural networks, there would be one neuron in the last layer. In quantum circuits, what we have is some other factor, quantum state, which is much more complicated than 1.11 scalar value. What is done is to measure an observable, define an observable. In this case, we have a total magnetization, and measure it. And this collapses the quantum state in one number. In this case, would be indeed, as I said, the total magnetization. And this is our f of x, or the approximation of the PDE solution. Now, for all of these, there can be various options, both for the encoding and for the depth, size, and form of the variational circuit, and of course also for the observable. And the interplay between these three determines both the expressivity of the network, so its ability to model in the first place a certain function, and also the trainability of the network, because in principle one quantum neural network could be able to represent one target function, but getting there may be harder or easier depending on the form of the variational part of it. Okay, I have hinted at the fact that circuit differentiation is possible in DQC, and the relevance of it, meaning that the loss function is exact, and this contributes to have a faster or a better gradient-based search of the optimal parameters. The costs hidden behind that is that this needs to be calculated, and of course, so there's more than one circuit to run. The first one to compute is f of x, which requires to do the measurement of the circuit I've just presented. So select a batch of points in the domain x, and for each of them, run a quantum circuit and do the measurement of the chosen observable. Then to compute the derivatives that go into the loss function, then additional quantum neural networks of the same structure, but with different parameters in the feature map need to be measured, run and measured. And lastly, also to compute the gradient, the same needs to be done, meaning running the same quantum neural network, the same circuit with shifts in the parameters in the variational circuit. So cumulatively, DQC requires to measure a number of circuits with several different parameters, but it is something that is equivalently done also in classical neural networks. And at the end, one has to do a balance between costs and an opportunity or advantage given by the method. Okay, and with this, let's say conclude my introduction to the DQC algorithm. With the last slide, I want to touch upon stochastic differential equations and how they enter the game. As said, DQC is an algorithm for solving partial differential equation, and it depends on the fact that this equation enters on the loss function. Now, stochastic differential equations are a different kind because they have a stochastic, a random term that determines a different outcome, a different solution at each time that let's say an iterative algorithm is run in order to solve this equation. So if we start from the same initial condition, there will be a plethora, a bunch of different solutions determined by the randomicity of the stochastic parameter of the equation. However, what one sees is that by propagating the wave, the function, a large number of times, this concurs to determine a distribution, and this distribution can be determined by, let's say, mapping the differential equation, stochastic differential equation, into a classical differential equation in which we have gotten rid of the stochastic term, and we have so-called, we have done the so-called, we have obtained a so-called quantized function or quantile function. And this quantile function responds to a classical then differential equation, which can be looped in. So we are back to the DQC algorithm. Of course, if one is interested in this distribution, that's one method which allows us to use the DQC algorithm. So aiming at identifying the distribution that solves the quantized equation, the Fokker-Planck. But there are other quantum algorithms, quantum methods that allow instead to generate this spaghetti here, this bush of solutions, and instead of obtaining the quantile function, well, populate it directly with a number of solutions of the same equation with different random elements. Okay, so with this, I conclude the first part of the presentation and move to challenges and research routes that we have faced and identified while applying the DQC algorithm to the various use cases. This is nothing but a little spoiler, because there will be a presentation on that on webinar 2. But I'll take the chance to mention the Burger's equation, which is a key model in aerodynamics. It's relevant because it is an approximation of the Navier-Stokes, and despite being a simplification, it features some relevant physical phenomena such as turbulence and nonlinear wave, phenomena like nonlinear waves. And we have been tackling this equation in collaboration, defining the problem in collaboration with Airbus, and studying it to begin with in one dimension, or I should say 1+1 dimensional systems, meaning one spatial dimension and propagation in time. Now, what we have seen, what we have obtained are mixed results. In some cases, we have seen that DQC was able to perform plug and play right out of the box and somehow approximate decently the target solution. Whereas we started to see some difficulties or some struggles in convergence when the problem showed that the solution showed kinks or accumulation of the profile, and this is the nonlinear type of phenomena that are manifested in the Burger's equation. As a matter of fact, we have also, we have tried a bunch of different initial boundary conditions, and the nonlinearity or the presence of steep profiles in the target solution definitely emerged as a problematic one or a challenging one for the DQC algorithm. So if in the previous case we were starting with sine functions and a large viscosity, not much happens besides a dampening of the amplitude. At low viscosity, these kinks appear, and the DQC algorithm is challenged. Whereas we have seen that if we start directly with initial boundary condition, which has already this kind of profile, then at times DQC was really converging towards the flat solution, which is a valid solution, at least for the interior, for the bulk of the domain. But of course, it does not satisfy the initial boundary condition. Therefore, it fails to reproduce the exact behavior. And I have mentioned this use case because indeed it's an interesting one, full of rich of phenomena and associated problems that come with it, such as this wave accumulation. And this has sparked a number of attempts at improving and enhancing the DQC algorithm in order for it to be able to perform well also with these equations and with these scenarios. Now, the first one that I'll mention is the trainable feature maps, in which the idea was to add a trainable parameter also on the feature map. So as I've said before, the idea is to have the training part in the variational circuit, because that's the, let's say, obvious one. The feature map is supposed to do the job of encoding the frequencies in the quantum neural network, whereas the training or modeling task is left to the variational circuit. However, the expressivity of the circuit is depending on the feature map rather than on the variational circuit. And a constant embedding, such as the one that I've shown before, that we try as a default one, implies that the frequencies available in a Fourier spectrum are fixed. It's there is a constant interval between two subsequent frequencies if one does a decomposition of the quantum neural network. And this may be suboptimal. It might be let's say suboptimal at capturing the profile of the target solution of the differential equation. So we thought of adding a variational parameter so that the frequencies of the spectrum of the neural network would be free to move and to adapt autonomously to what is the best combination that helps enhance the expressivity and model better the target solution. And we have actually applied this to a number of problems inside and outside of the equality endeavor. We are going to present results, I guess, also next week, including trainable feature maps for problems designed within the equality consortium. But let me show you these plots from a paper that has come out last year, in which a team at Pasqal has been studying the incompressible Navier-Stokes in a steady state form, so as a function of x and y and no dependence on t. And if on the left-hand side you see the reference solution obtained with finite element methods, on the right is the best that quantum neural network could do with fixed Fourier feature maps. And we have seen quite an improvement by using trainable Fourier feature maps that allow it for a more flexible expressivity of the circuit. Now, this is also not exact copy of the FEM reference solution, but it definitely marks an improvement over the basic QNN. And okay, let's see. Yes. Along the same line, we have been conducting some studies, some analysis of the expressivity, more thorough, in order to more clearly capture the impact of having trainable frequencies or the restrictions of non-trainable frequencies when they perform fairly well, when not, and why. So, and one simple way to understand the type of questions that we have been asking and the type of analysis that we did is to look at this profile here as it evolves, and the corresponding Fourier spectrum, which at the beginning is quite fairly contained in the number of frequencies that are needed, between -15 and 15 roughly covers the whole distribution of the frequencies, amplitudes, whereas as the wave propagates and there is an accumulation in nonlinear phenomenon, in this case, I think it was the Burger's equation as well, then of course the spectrum broadens and it requires many more frequencies in order for the quantum neural network to model properly the function in its entirety. We see that it's still able to capture properly the flat part of the function, but the steep part is not well reproduced. And there are in the literature articles and studies that demonstrate the strict connection between expressivity and number of available frequencies, available modes, and the number of qubits, or rather the number of encoding operations in the feature map. Now, these and other aspects of the encoding, the feature maps, the quantum neural networks are then subject of investigations that we are doing in order to be able to tell beforehand whether a network is at least expressive enough to represent a certain function. And this can be guessed based on, estimated based on arguments such as the relation between width of the spectrum and number of encoding operations. Okay, with this, I conclude the part related to the algorithm and come to talk a bit about the hardware, in particular, being Pasqal a quantum company producing hardware based on neutral atoms. I will give a brief presentation on this architecture and and how this allows to run digital quantum algorithms. So a quantum computer, neutral atom-based quantum computer, is a machine that looks like the one in this picture, has this size. In particular, this is Fresnel, the machine that Pasqal has already delivered to a number of clients and installed in supercomputing centers in France and Germany. It notably is a setup, in general, this is a thing of neutral atom architectures, not only Pascal's. It is a setup that works at room temperature. There is no need for cryogenic. There is only need for a good vacuum void environment with extreme vacuum. And yes, it is built notably out of industrial off-the-shelf components. So it's no longer a table full of cables and optics, and that takes 2 postdocs and 3 PhDs to run and to keep running. It is an industrialized product, which notably also uses very low energy, which is quite an argument, especially considering the impact of the energy, how energy greedy is quantum machine learning. Because if, let's say, an impact or some form of quantum advantage can be demonstrated on, based on quantum computers, then let's say the product is ready and it is even easy to install at clients' premises. Now, how this works in a nutshell is that there is a vacuum chamber where about 10 to the 5, 10 to the 6 atoms are loaded, notably rubidium, but can be also other atomic species. And then through mirrors, lasers are let in. And lasers are all it's needed for these atoms to be trapped in a regular array, which becomes then the register, and where we do the operations that correspond to the quantum algorithm. In particular, if we look at the central zone where this laser is shining, we see that the main laser, which is one single laser reflecting back and forth, is then split by a mask into a number of smaller laser beams. And for a principle, a law of physics, the atoms, neutral atoms, tend to prefer regions of where the intensity of the beam is larger, and these beams have a certain Gaussian profile, so they're stronger at the center, which is in this region here, and therefore if an atom accidentally, let's say, passes by and it's not too fast, it's already slow enough, then it can remain trapped in this so-called tweezer and maybe oscillate a little bit longitudinally and transversally, but it is trapped in there. And so the trapping, the initial loading is random. So we cannot know which of the many tweezers arranged in a regular grid will trap one atom. But then the same lasers that trap are also able to, a bit more slowly, but yeah, using caution, but with nearly 100% efficiency, transfer these atoms from one site to another one. This process is called rearrangement and allows to distribute the atoms nearly at will. Okay, now once we have an array, a register of atoms, we want to do operations with them. And again, in order to do that, we look at the quantum algorithm and see that, oh, here there is a C0 between atom 3 and atom 5. And where are they? Maybe they are distant from one another. So we take this oversimplification, but take atom number 3, move it closer to atom number 5, and, well, nothing will happen because these atoms are neutral and they do not interact with one another. However, if they're both with a certain specific sequence excited to a Rydberg state, which is a state that has a very large electric dipole, then they communicate, they talk to each other, and this enables the realization of an entangling gate, in particular the CZ gate, which is equivalent up to single qubit rotations to the C0. And we know that all it's needed is 1 and 2 qubit operations for universal quantum computing, and this is available in neutral atom quantum computers through the protocol based on excitation and to the Rydberg state and decay back to the ground state. Note that the ground state is split in well, there are 2 hyperfine states that represent the 0 and 1 state of quantum state, the qubit state, whereas the Rydberg is only functional for realizing the entangling gate. Okay, so at the end of the run, the atoms will be in a regular array, a square, or maybe another one, and some of them will be in 0, in 1, or, well, they will actually be in a more complicated state, but we need to measure them, and by measuring them means we are projecting them either on 0 or 1 state. And this is done with a global, another laser, another pulse that basically blows away, let's say, the ones, or in other words, only shines on the 0, makes them fluorescent. So if this is the let's say distribution of 0 and 1s on the register, what we see, literally see it because it's light emitted by the atom, is the 0s, and then you can assume that the other ones are 1s. Of course, there will be some leakages, some particles here will be actually lost, so it was not a 1, but this is part of the errors that we are committed to improve upon, and in general make the machine better and better. Now all this cycle occurs in less than a second. It is known that neutral atoms are not as fast as other platform like superconducting qubits, but they have other perks, which are the scalability and the ease in arranging and controlling the atoms at will, basically. So within nearly less than a second, a whole cycle is completed, and this means that the atoms are loaded randomly in the register and then rearranged in a smaller area, the register where the operations are done, and then there is the readout, the imaging, which I've just talked about. Yes, as I was saying, the perks is the most notable one is the scalability of the platform to a large number of qubits, and which builds upon more than 2 decades of research and know-how in academia, in research labs, as to how trap atoms, control them, maneuver, excite them, change the state, and so on and so forth. And as you can see from this slide, the growth in number of qubits has been impressive over a decade, out of which basically the last less than 10 years definitely has seen the birth of quantum computing companies whose architecture is based on neutral atoms, and before it was largely academic research. All right, and with this, I think I conclude my presentation for today. I'm happy to take questions.